Section 8.5 is on partial fraction decomposition. Partial fractions is not really a technique of integration, it's more of an algebraic technique that we use to break up common denominators in a rational expression. So the process of partial fraction decomposition is mostly algebraic, and then once I get to a new simplified integrand that I've used partial fractions to get to, then I use all the old techniques of integration that I've learned up to this point. So first of all, let's go ahead and look at the procedures or the steps involved in partial fraction decomposition. Partial fraction decomposition can only be applied to rational expressions. So we need a rational expression, and of course a rational expression means it has a numerator and a denominator. So some numerator over some denominator. So this does not work on this does not work on radicals, exponentials, trig functions. This only works on rational expressions, and whatever's in our numerator and denominator is typically some sort of a polynomial expression. So once I've identified that I indeed have a rational expression, the first thing I do is I make sure that the degree in the numerator is less than the degree in the denominator, meaning I don't want my fraction to be top heavy. I want to make sure that I have a proper fraction. Now, the way that you're going to fix this if this is not true is by using long division. Now if you want to use long polynomial division or synthetic division, use what you want, but sometimes you have to use long polynomial division, so it's a good idea to be aware of that process as well, because not all of my denominators are going to be a nice little linear term to divide through by. So if the degree in the numerator is less than the degree in the denominator, we're fine. We can go ahead and go to the next step. If the degree in the numerator is greater than or equal to the degree in the denominator, I have to use some sort of long division in order to simplify the expression. The next step is to factor the denominator completely. And when we say completely, we mean completely. It has to make sure that there's no greatest common factor, there's no common x or anything like that that I can pull out. So it's very important to factor the denominator completely. Now what we like to do is we like to factor it into linear terms or irreducible terms. The next thing we do is we decompose the fraction. That's why it's called partial fraction decomposition. So we decompose the fraction. Now by decomposing the fraction, what we mean here is we mean separate it out into its terms. And there's basically two types of terms that we're going to be looking at. First of all, we could have some sort of a linear term in the denominator, and if we had some sort of a linear term, I would decompose it as such. And I could have up to n terms here. Now, if we look at a linear term, if we think about, let's say, like the derivative of a linear term, the derivative of a linear term is a constant, so we're going to be looking at one less degree than linear as a constant. So our numerators here will be some constant a, some constant b, all the way up to some constant z. Now one thing that we need to be aware of are these values of lowercase a, lowercase b, etc. Those are going to be numbers. These cap a, cap b, cap z right now are variables that we're going to be solving for. Next we have to look at not only our linear terms, but we have to look at our quadratic terms as well. Now in terms of a quadratic term, we know the general equation for a quadratic is ax squared plus bx plus c. And we'd write out all of the quadratic terms we'd have. And it's not guaranteed that we'll have a quadratic term, but if we do, this is how we would work with them. This is to the nth. Now, what's one less than a quadratic? Well, quadratic is to the second power, so one less than the second power is to the first power. So here I would have some linear term in my numerator. And again, I'm going to be solving for these values of a, b, c, d, etc. Now what we want to do is we want to reassemble the fraction using a common denominator and equal numerators, and we don't want to expand this. And then what we'll do is we'll solve for these values of a, b, c, d, all the way up to however many variables we have by substitution, and then we plug in for x into these values and we integrate what results. So I think the easiest way to actually talk about these is by looking at an example. So for this example, first thing we always do is try and use a nice u substitution, because if a u sub will work, it's a lot easier than doing all this partial fraction or integration by parts and whatnot. So first of all, will a u sub work? Well, in this case, u would equal x squared plus x minus 6. du would be 2x plus 1. I don't have it. Can't get it, so I'm not going to be able to use a nice u substitution. So what I'm going to do is I'm going to pull this integrand out and see if I can perform some partial fraction decomposition with it. Okay, so I'm going to drop the integral for now, and we're just going to work on some algebra. So this expression of 5 divided by x squared plus x minus 6, I'm going to look at in its decomposition form, and I'm going to think about how this would factor. Now remember, x squared plus x plus 6 is a product of binomials. X and x, I think this would go with plus 3 and a minus 2. So that tells me that the linear factors here are plus 3 and minus 2. And you might say, well, wait a minute, we can't do this because here I'm not multiplying these together. But if you were to find a common denominator, that's exactly what we'd be doing. We'd be multiplying these together. And so that's what we're trying to do, is we're trying to write this single rational expression split off into its two terms that I would find a common denominator with. Now the way this works is both of these are linear. If I were to graph x plus 3 and graph x minus 2, they are linear. So if I have a linear base, I need a constant numerator, in this case for a and b. Then what I do is I solve for cap a and cap b and rewrite my fraction, and then hopefully I should be able to integrate it. So let's go ahead and look to see how we do that. I'm always very careful about not dropping this side, because on this side is where we need to actually use this value of 5 to solve. So what we're going to do from here is we're going to go ahead and find a common denominator. That common denominator is the product x plus 3 times x minus 2. So for this one, I'll multiply top and bottom by x minus 2. So I'm left with a times the quantity x minus 2 plus b times the quantity. Here I'll multiply top and bottom by x plus 3. And this is all over my new common denominator of x plus 3 x minus 2. Now if you notice, we have an equal sign here. We have an equal sign. So because I have this equal sign, what we're going to do then is we're going to say, okay, now that this is an equivalent statement, the denominators are equal. If the denominators are equal, I can ignore the denominator and equate the numerator and work with that in order to find those values of a and b. So I come up with this new equation, 5 equal ax minus 2a plus bx plus 3b. Now my goal here is to try and solve for a and b. There's a lot of different ways we can do this, but if we can, it's really easy if we can equate the coefficients. For instance, I can group my x's together, and then I can group my constants together. If we group my x's together, I have a plus b x, and that's reverse factoring here, plus 3b minus 2a. Now if you look over here, I don't have any x terms. Let's see if we can write that a little bit better. I don't have any x terms. So one way I could rewrite this on the left-hand side is to say this is 0x plus 5 is equal to a plus b quantity x plus the quantity 3b minus 2a. Now if this equality is actually true, that tells me whatever the coefficient is on the left in front of my linear variable better be equal to the coefficient on the right in front of my linear variable, and whatever my constant is on the left has to equal my constant on the right. So this is called equating coefficients. So the way this would look then is that a plus b would equal 0, and 3b minus 2a would equal 5 then. So this is equating the coefficients. Now what I have is two equations and two unknowns. There's a lot of different ways to solve this. I'm going to solve this by substitution. So I'm going to say that a is equal to negative b. And then I'm going to plug that in over here and solve. So again, a I said was negative b. So I have 3b plus 2b equals 5. 5b equals 5, or b equals 1. Okay. So if b equals 1, that implies that a equals negative 1 by substitution as well. So I have my new integrand to write. So now I have the integral of my decomposed fraction. I had x minus 2, let's go back up here and look. I had right here x plus 3 and x minus 2, so I had a over x plus 3 and b over x minus 2. Well, a was negative 1, b was 1, and now I should be able to integrate. Well, both these integrate into nice natural logs. So in this case I have u equal x plus 3, du is dx, u is x minus 2, du is dx. So again, each of these integrates into a nice natural log, absolute value of x plus 3 minus natural log absolute value of x minus 2 plus c. Now sometimes you'll see this written a little bit differently because this is a log x plus 3 minus log x minus 2, and we know the log of a quotient is the difference of the logs, and so the difference of the logs should be able to be rewritten as the quotient. So we have x plus 3 over x minus 2 plus c. So that's how that integrates. So partial fraction decomposition is basically working an algebra problem that you've worked hundreds of times backward. So instead of starting with my fractions on here on the right and finding a common denominator, I'm starting with the common denominator and trying to break it down into the fractions that it came from. So again, most of this is algebra. Let's go ahead and look at another example. And these are long. So remember, you just have to kind of stick to it and make sure you remember what you're trying to get at the end. Let's go ahead and look at the integral of 4x squared plus 3 in my numerator, and in my denominator x minus 5 quantity cubed dx. Now the first thing I want to do is I want to check, is the degree in the numerator less than the degree in the denominator? And right now it kind of looks like maybe not. The degree in the numerator is a 2 because of this 2 right here, and the degree in the denominator, you might look at that and say, oh, it's 5, but it won't be after we expand it. If we were to expand this, we can see that it actually be x cubed. So 2 is less than 3, so we are ready to go. So again, it's not always real obvious, so sometimes you have to double check for that. So the next thing we want to do is we want to decompose those fractions into their terms. We want to factor it completely. Now I have 3 as my exponent here. That means I should have 3 decomposed fractions that I'm working with. So I have to have a left-hand side in my equation to equate here. This is x minus 5 quantity cubed. And on the right-hand side, I have to write all of the factors of x minus 5 quantity cubed. Well, the factors of x minus 5 quantity cubed, there's 3 of them. X minus 5 to the first, x minus 5 squared, and x minus 5 cubed. Now if you look at the base of each of these, the base, each of these bases is linear, and because each of the bases is linear, that tells me that the numerator has to be some sort of a constant, and the constants we use are a, b, and c. Now what I do is I take this right-hand side and I go ahead and go through and find a common denominator. Well, my common denominator has already been given to me. It's x minus 5 cubed. So this is going to look like x minus 5 squared, top and bottom, to get that common denominator. This will look like x minus 5 to the first. And this already has the common denominator, so I don't need to do anything there. Now once you have that common denominator, you can drop it and just equate the terms of the numerator. And I'm left with a, x minus 5 quantity squared, b, x minus 5, c. Now again, there's a lot of different ways that we can work this type of a problem. For instance, if I plug in x equal 5, right away a and b will go away because 5 minus 5 is 0, and I should be able to solve for c. So before I equate coefficients, that might be a nice little intermediate step in order to try and figure out what at least one of my variables are. So I'm going to go ahead and let x equal 5 here and see if that helps out with some stuff. So if I let x equal 5, on the left-hand side I have 4 times 5 squared plus 3. On the right-hand side, when I plug in 5, of course, much of this is going to go towards 0. So on the left-hand side I have 5 squared is 25 times 4 is 100 plus 3 is 103. And on the right-hand side, 5 minus 5 is 0. 5 minus 5 is 0, that should have been a 5 there. So I'm left with c equals 103. So one of our numbers is pretty big here. So up here, I already know that c is 103. Now I need to figure out what a and b are. Okay, so in order to figure out what a and b are, let's go ahead and look at equating the coefficients. Again, there's different methods we can use, but these are just some real easy basic algebra approaches that we could have here. Now that we know that c is equal to 103, we can write out this equation again. So we'll have 4x squared plus 3, write out everything as before, but in place of c we'll put 103. Now what we're going to do is to expand this, so we'll take x minus 5 squared, we'll FOIL that out, distribute the a, distribute the b, and then go ahead and group things in terms of linear or quadratic or constant terms. Okay, remember with the expansion, you go ahead and FOIL this out, you don't distribute through the 2. So here's our expansion, and in our next step we'll go ahead and group our constant, linear, and quadratic terms. So when we group our terms, we'll notice here that we have a is our x squared, so that's our quadratic coefficient. I have negative 10a and b with an x term, so that's my linear coefficient. And then everything else is constant. There's no x involved in it. So when I look at the right-hand side here, I see, oh, I have a quadratic, I have a linear, and I have a constant. Well, on the left-hand side, I don't have a linear. So let's go ahead and rewrite that. Now when we rewrite the left-hand side, I can start thinking about equating the coefficients. If these are truly equal statements on the right and the left, then my 4 had better equal a. My coefficients better match up for my quadratic terms. My coefficients better match up for my linear terms, so 0 better equal negative 10a plus b. And 3 better equal the constant on the right, which is this trinomial. So that's the next step, is to go ahead and equate these coefficients. So as soon as we equate these coefficients, we have another solution. We know a is equal to 4. So if we look up from above, we have c is equal to 3, and now we know a is equal to 4. Okay, so we have c is equal to 103, and a is equal to 4. So it looks like all we need to do now is to find b. So we can substitute in. A equals 4, I can plug in right here. Negative 10 times 4 plus b. I get negative 40 plus b equals 0, add the 40 across, and I get b equals 40. And so now I know a, b, and c. Now did I end up needing this one? No, I didn't, because I already know a and b. But let's go ahead and check and see with what we did if it's going to equate. So 25a, a is 4, b was 40, plus 103. So again, what we're trying to do is to perform a check to see if this is actually equivalent. So here I get 3 equals 100 minus 200 plus 103. 100 minus 200 is a negative 100 plus 103 does equal 3. So this does check, but again, we didn't have to actually do that. So to summarize, we have a equal 4, b equal 40, and c was equal to 103. Well, now what we do is we come back up to our top and we plug those into where our positions of a, b, and c were. And that's going to be my new integrand, and then hopefully I'll be able to integrate from there. So we have 4 over x minus 5 to the first, and I'm going to separate these into separate integrals right now. b is 40 over x minus 5 squared, and c was 103 over x minus 5 cubed. Well, all of these will easily integrate with a nice little u substitution. U is x minus 5 for each one of these. Du is dx. U is x minus 5. Du is dx. U is x minus 5. Du is dx. But they don't all integrate into natural logs. This first one that we're going to be looking at, this is equal to 4 natural log absolute value of x minus 5. Okay, because it's a 1 over u to u. This next one, I'm going to go ahead and pull that 40 out front. This is going to be 40 over u squared. 40 is pulled out front. 1 over u squared, I'd flip that up top to u to the negative 2 to u. And this next one, 103 out front, would be u to the negative 3 to u. And of course, to integrate these, you add 1, divide by the sum. So when you add 1 to my exponent, I get negative 1 is my new exponent divided by negative 1. Here I'm going to get u to the negative 2 divided by negative 2. So rewriting, I even forget what our original was here. 4x squared plus 3 over x minus 5 quantity cubed. I'm getting 4 natural log absolute value of x minus 5. Okay, minus 40 u to the negative 1, but u is x minus 5, minus 103 over 2 x minus 5 quantity squared plus c. And of course from here you can find a common denominator and simplify, but I don't think much would simplify, so I'm not going to really look at that one in this case. Now in Maple there's a function called parfrac, and you can go ahead and look for that under the help menu, and it will find a partial fraction for you to kind of double check your work if you're having troubles finding those coefficients. Now these are very, very long problems, and they do take quite a bit of space. Let's go ahead and look at another example that's probably going to be even a little bit longer than the previous examples because I have some quadratic terms involved. Let's go ahead and look at the integral of 2x minus 1 in our numerator, and in my denominator I'm going to have x times x squared plus 1 quantity squared dx. Okay, first thing we want to check for is the degree in the numerator less than the degree in the denominator. Well, the degree in the numerator is 1. The degree in the denominator you might think is squared, but really it's going to be squared squared times x, so that's going to give us a 5 here. And 1 is less than 5, so I'm good to go. Now, if this had not been the case, I would have to use long polynomial division first, and then use the method of partial fraction decomposition. But I don't have to on this one because the degree in the numerator is less than the degree in the denominator. So the first thing I'm going to do is go ahead and look at factors of the denominator. The factors of the denominator in this case are x, x squared plus 1, and x squared plus 1 quantity squared. Now if you multiply all three of these together, you do not get the denominator back. I'm not asking for what are the single factors of the denominator. I'm looking for like a prime factorization, and when you look at the prime factorization, this x squared plus 1 factors out into x squared plus 1, x squared plus 1, so it does count as one of those factors of the denominator. So I have 3 factors of the denominator, so I'm going to have 3 partial fractions that I work with. So again, we always keep the left-hand side here as well, because that's how I'm going to equate coefficients or solve for some of these fractions. And I go ahead and rewrite. So I have x squared plus 1 to the implied 1. I'm just going to sketch that in. It's to the implied 1. And of course it's not needed. And then of course our last one here is x squared plus 1 quantity squared. Now this first one is pretty easy to work with. This is a nice x. It's a nice linear term. Now if I have a linear base, I have a constant numerator. Now here, if we just look at the base, x squared plus 1, this is a quadratic base. If I have a quadratic base, I need a linear numerator. So I'll have a b x plus c. So I'm going to be solving for a, b, and c here. Now on this next one, what is my base? The base is x squared plus 1, which is a quadratic. I've used a, b, and c, so now I start up again with d x plus e. We usually use capital letters here, so make sure you're using those caps to represent the values that we're trying to solve for. Now I want to solve for a, b, c, d, e. That's 5 unknowns. So if I have 5 unknowns, you might think, well, we need 5 equations. Okay, that would be one approach. Or we can try and start singling these out a little bit. For instance, if I were to plug in, let's maybe start with x equals 0. After I find my common denominator, I might be able to figure out one of my variables right out front. So the first thing, let's go ahead and look at finding that common denominator. So again, drag that left-hand side along. Whoops, squared. And then in my numerator, I have 2x minus 1. Okay, now I need the common denominator of x times x squared plus 1. I already have the x. I need to multiply top and bottom by x squared minus 1 here, or sorry, x squared plus 1 squared. So again, I need to multiply top and bottom by x squared plus 1 here, quantity squared. Okay, let's look at our next one. In my next one, I already have x squared plus 1 to the implied 1. My numerator, I already have my bx plus c here. I need another x squared plus 1, and I need an x to get that common denominator. Okay, and in my last term I have this dx plus e. In my denominator I have x squared plus 1 quantity squared. What am I missing here? Well, here I'm missing the x, and so I multiply top and bottom by x. This looks like a big old mess, and it is, until we do a lot of algebra, and then it will start looking quite a bit better. So let's go ahead and write this out. Now notice we already have a common denominator here and here on the right. So once I have a common denominator, what I can do is drop the denominator and just equate the coefficients in the numerator, or set the right and left hand sides equal in the numerator. So I have 2x minus 1 equals a times x squared plus 1 quantity squared. Here I'm going to leave this x out front and we'll write this bx plus c times x squared plus 1, x out front, dx plus e. Now I noticed something here. Every single one of these terms has an x in it except for a. Here's the x here, here's the x over here. So I could probably get rid of one of my variables by letting x equal 0. So if we let x equal 0 over here on the left hand side, I have 2 times 0 minus 1. And on the right hand side I'll have a times 0 squared plus 1 quantity squared plus, well, what's going to happen here? Once I plug x equals 0 in, that whole term goes to 0. Same thing here, that whole term goes to 0. So it looks like I'm left with, on the left hand side, 2 times 0 is 0, minus 1 is negative 1. And over here, 0 squared plus 1 is 1, squared is 1, times a is a. So I get a equals negative 1. So I got one of my coefficients, 1 out of the 5. And I have 1 out of the 5, so I have 4 more left. But at least I have one good one to start with. Like I said, these are very, very long problems, so let's go ahead and keep track of what we've done so far. Since I know a is negative 1, I'm going to come up and plug that in right here so I can kind of keep track. A is negative 1. Now what I can do is I can plug a equal negative 1 in right here and then go ahead and expand and see if I can get anything else out of this that might be easy to solve for. So that's my next step. I'm going to plug a equals negative 1 into this expression. So I'll be left with 2x minus 1 equals negative 1 times x squared plus 1 quantity squared. And I'm going to just rewrite that out because we're going to want to expand this anyway. And we're going to want to start expanding up here as well. So I'm going to distribute through the x to begin with. So I'll have bx squared plus cx times x squared plus 1. And then of course distributing through the x over here will be easy. Dx squared plus ex. And again, I'm all algebra, just expanding. 2x minus 1 equals. If I expand out x squared plus 1 quantity squared, I have x to the 4th plus 2x squared plus 1. And then I need to distribute the negative. So I have a negative x to the 4th, negative 2x squared minus 1. Okay, then I need to FOIL this out, first outside, insides last. So I have bx to the 4th plus cx cubed plus bx squared plus cx, and then of course plus dx squared plus ex, dragging those along. Okay, that took a while. Now, what I want to do is group all my like terms together. I want to have all the x to the 4ths together, all the x cubes, all the x squareds, all the x's, all the constants. So that's my next step. Another thing I note is on the right hand side here, my highest power is to the 4th degree. So over here on the left hand side, I don't have a 4th degree polynomial. So 0 would be the coefficient in front of my x to the 4th term. 0 would be the coefficient in front of my x to the 3rd term. We don't even have a squared term over here on the left. So I'm going to have another 0 is the coefficient in front of my x squared term. Now I'm down to my linear, so now I'll have a 2 in front of my linear term, and then of course my constant here is minus 1. All these zeros kind of make things a little bit easier, but not necessarily. So this left-hand side has been rewritten as such, and this is going to be equal to, and there's no way I'm going to fit it over here, so I'm going to start underneath over here. Now, in terms of my x to the 4th, I have a negative x to the 4th plus bx to the 4th, so I'm going to group that together. So I'm going to get a negative 1 plus b as the coefficient in front of my x to the fourth term. My next one that I'm going to look at here are my third degree polynomials, and I only have one third degree, so it's plus c. That's good. So we only have one term, it's easier to equate these. X to the third. Okay, my next one I'm going to be looking for squareds. So I have a negative 2 plus b plus d. Negative 2 plus b plus d x squared. Okay, now I'm looking for linear, and for linear I see cx plus ex. So I'll rewrite that down here. C plus e x, and then I'm left with my constant. And is there a constant? Yep, there is. There is a constant right here, and that's minus 1. And this looks really good because I have a negative 1 for a constant on my right and a negative 1 for a constant on my left, so this is working out pretty good. So now let's go ahead and equate the coefficients. I don't think we need quite that big of a stylus. So let's go ahead and equate the coefficients. Now when we're looking at equating the coefficients, whatever is in front of the x to the fourth term on the left has to be in front of the x to the fourth term on the right if they're equal. So I have 0 equals negative 1 plus b. I have 0 equals c. I have 0 equals the term in front of my x squared, which is negative 2 plus b plus d. I have 2 equals c plus e. And, of course, my constants, I have negative 1 equals negative 1. I really don't need to write that, but it's a nice little check. So now I start solving, and these will go pretty fast now. Solving for b here, I get b equals 1. Here I have c equals 0. That's nice. Now over here, I can't solve quite yet before I substitute. So I need to substitute. So b equals 1. So I have 0 equals negative 2 plus 1 plus d. 0 equals negative 2 plus 1 is negative 1. D equals 1 here. So I have A up top, B, C, D. Now I need E. Well, I know C is 0, so E must be 2 in this case. So now I have all my other coefficients. B equal 1, 0, 1, 2. 1, 0, 1, 2. So now I put those all up top in my original up here. So A was negative 1, we already figured that out. B is 1, C is 0, which is nice, it makes your integration easier. D is 1, and E was 2. And that's what I'm going to try and integrate now. So let's go ahead and scroll down, rewrite our integrand, and see what we can come up with. Okay, remember we were trying to integrate this to begin with, and I'm going to separate these out. We had A, which was negative 1 over x, plus cx plus d, or sorry, bx plus c, which was 1 times x plus 0, because b is 1, all over x squared plus 1 to the implied 1. This will be a nice little 1 over u du after we do a little work there. And our last one here is going to be dx plus e, which was 1x plus 2, and this is all over x squared plus 1 quantity squared dx. So we have a lot to keep track of here. Some of these will integrate easier than others. This first one is particularly true of that. This first one is just minus natural log absolute value of x. It's nice to have an easy one. This one, let's go ahead and rewrite and work on it. I have the x in my numerator, x squared plus 1 in my denominator. U is x squared plus 1. Du is 2x dx. So I multiply by 2 on the inside, compensate with a 1/2 on the outside, and this looks like 1/2 the integral of 1 over u du then, which is another natural log absolute value of u. This u is x squared plus 1. So this one integrates into 1/2 natural log absolute value of x squared plus 1. Now this last one, let's see what we can get for it. First of all, let's go ahead and rewrite. In rewriting this, I have x plus 2 over x squared plus 1 quantity squared dx. Now we're going to have a look at this. This one is not going to be super obvious on how we're going to integrate this. If we look at this in terms of separating the numerator, I think we'll have better luck. So let's look at this as x over x squared plus 1 quantity squared plus 2 over x squared plus 1 quantity squared. So we're separating the numerator. Remember, you can never separate the denominator. Since we split this up into two integrals, let's go ahead and look at this again and split it out again into two separate integrals. So let's go ahead and look at this first one first. Remember, it's important to keep track of all the other things you've already integrated. So here we have x over x squared plus 1 quantity squared dx. This is a nice u substitution. U is x squared plus 1. Du is 2x dx. You multiply by 2 on the inside, compensate with the 1/2 on the outside, and this is 1/2 integral u to the negative 2 du. We integrate, drag along the 1/2, you add 1, divide by the sum. So this integrates into negative 1 over 2u, which was x squared plus 1. So again, we have to keep track of that. Negative 1 over 2 x squared plus 1. So negative 1 over 2 x squared plus 1. Now there's going to be something else here though, because remember I split this up into two separate integrals. So let's go ahead and look at this piece next. This will be the integral of 2 over, I'll pull the 2 out front, so we'll look at 1 over x squared plus 1 quantity squared dx. Now you'd think these problems would be getting a little bit easier instead of harder, but now we're kind of stuck again. How do I integrate this thing? Is it another trig sub? Is it another partial fraction? You know, what could we do here? Well, the answer is it works out to be a nice little trig sub. Now remember, with a trig sub, if I have something of the form u squared plus a squared, the recommendation is just to let u equal a tan theta. U in this case is x, a is equal to 1, so x is equal to 1 tan theta. Dx is equal to the derivative of tangent squared then, which is secant squared theta d theta. So that's the substitution I'm going to want to make up here. So I'll make these substitutions back up in here. So I have the 2 out front. Dx is equal to secant squared theta d theta. Now my denominator is going to be x squared, which is going to be tangent squared theta plus 1 quantity squared. And again, it's all algebra from here. I have the 2 out front, dragging along the secant squared theta d theta. And in my denominator, remember, Pythagorean identity here, 1 plus tangent squared is secant squared squared is secant to the 4th theta. Dragging along the 2, this is going to leave me with 1 over secant squared in the numerator. But remember, 1 over cosine is secant, so 1 over secant squared, I can flip that up top, and this becomes 2 integral cosine squared of theta d theta, which we can integrate because we have a half angle identity. Cosine squared is 1 plus the cosine of 2 theta all over 2 d theta. 2's cancel. Man, these are fun problems, but they're kind of long too. Integral of 1 d theta plus the integral of cosine 2 theta d theta. Well, this piece is easy enough. The integral of 1 d theta is theta. The integral of cosine 2 theta, I let u equal 2 theta. Du then is 2 d theta. I multiply by 2 on the inside, compensate with 1/2 on the outside, and this piece ends up looking like 1/2 the integral of cosine of u du, which is 1/2 sine of u. U is 2 theta. So this piece looks like theta plus 1/2 sine of 2 theta. We have a nice little helpful identity here that will rewrite this for us. We know that the sine of 2 theta is equal to 2 sine theta cosine theta. So this ends up looking like the 2's are going to cancel. Theta plus sine theta cosine theta. Now from here we need to go back to our original substitution and talk about that right triangle. Now the substitution that we made originally was we let x equal tangent theta. And it was actually x equal 1 tangent theta. This is the same as tangent theta equals x over 1. Remember, for your right triangle SOHCAHTOA, tangent is equal to opposite over adjacent, so that would make this missing hypotenuse x squared plus 1, of course, square rooted. Then from here to solve for theta, we can use an inverse trig function. Theta is equal to the inverse tangent of x, and if you want to put x over 1, you can. Sine is equal to the opposite over the hypotenuse, which is x over root x squared plus 1. That's the sine of theta. And cosine of theta is adjacent over hypotenuse, which is 1 over root x squared plus 1. Now that's only the solution to this in piece, and we still need to recombine all of these. And I guess actually we could rewrite this just a little bit. For this piece right here, this is just equal to the inverse tangent of x plus x over x squared plus 1. Okay, I'm not even sure where this goes. Let's go ahead and scroll up. See if we dropped anything along the way. We had our trig sub there. Well, here's this piece. We had negative 1 over 2 x squared plus 1, and we have that in here. And then from the trig sub we just did, we have plus inverse tangent of x plus x over x squared plus 1. So we should be able to take this and rewrite all of it combined. So rewriting, let's go ahead and take this big piece right here, and let's rewrite it nicely down here. See what we've come up with. Okay, so we have the integral of 2x minus 1 over x times x squared plus 1 quantity squared is equal to minus natural log absolute value of x plus 1/2 natural log absolute value of x squared plus 1 minus 1 over 2x squared plus 1 plus, and we're right here, inverse tangent of x plus x over x squared plus 1 plus c, constant of integration. That's my solution. Took a while to get there. Now if you were to do the same problem in Maple, you might not get the same answer, but you should have equivalent expressions. So that's one of the important things to remember, is your expressions should be equivalent. Good luck with these problems. They do take a while. I'm going to post up a different video with more problems worked. If you want to watch more problems, you can, but if you have enough to get going, that's great too.